Let's have a look at the answers then to this GCSE Chemistry paper higher tier Unit 2. Question 1A then, explain how a catalyst affects the rate of reaction or increases the rate of reaction. Now this is not stating what a catalyst is, which would be a substance that speeds up a chemical reaction without getting used up. So you have to explain how the catalyst works. So it provides an alternative reaction pathway, and don't say alternate reaction pathway. Again, reaction is also important, of lower activation energy. At what time did the reaction finish? So I'm just going to skip 39 to 41 seconds. Make sure you put in your units. Part 2, what is the total volume of gas produced? The units. Part 3, sketch the line you'd expect to obtain if the experiment is repeated at 25 cubic centimetres, the same volume, but the concentration has changed. It's 0.1, and the mass has stayed the same, and the catalyst is the same. So we know that the concentration has decreased. It was 0.15 to start with, so I'll just put in 0.15, it would be moles per cubic decimetre, and it's going to 0.1 moles per cubic decimetre. Now before I answer this one, I want to consider the way these reactions usually are, and that is that they involve two reactants. For example, calcium carbonate reacting with hydrochloric acid. So here we've got two reactants, and if you change the concentration of the hydrochloric acid, so let's say we decrease it, so it's the same as what's happening in this reaction, then the graph would look something like this. And so just draw it, I'll just sketch it here. Start off at the same place. Because the concentration is less, the rate of reaction would be less, the line would be less steep, but it would level off at the same place. So that's if we keep everything the same, and that's for two reactants. We've just changed the concentration, we've lowered the concentration. But in the question for this exam paper for hydrogen peroxide, it's slightly different, because the hydrogen peroxide is the only reactant, and the oxygen that's made comes entirely from the hydrogen peroxide. So this is the equation. Remember, you'd use manganese dioxide or manganese 4 oxide as a catalyst. So as I said, all of this oxygen comes from the hydrogen peroxide. So if the concentration is decreased, that means that less oxygen will be made, so it doesn't level off at the same place. So in other words, it doesn't level off at 45 cubic centimetres. So that's the difference between this one, where you've got one reactant, and that previous example, the calcium carbonate and the hydrochloric acid, where you have two reactants. So it's going to start off at 0, 0. It's less steep because there are going to be fewer particles, so fewer successful collisions per unit time. But you have to figure out where to level it off. Now, the original was 0.15 moles per cubic decimetre, and that produced 45 cubic centimetres. Now we want to get to 0.1 moles per cubic decimetre. So what you can do is divide by 0.15 and then multiply it by 0.1. So you do the same thing here. So it's going to be 45 divided by 0.15 times 0.1. And that gives an answer of 30 cubic centimetres. That's where it has to level off. So then it continue up and then along. Part C, then we have to calculate the energy change for this reaction. So I'm just going to do a simple table here for bonds broken and bonds made. And then we have the bonds broken. Well, you can see that there's an OH. Now 2, 3, 4. So there are 4 OH bonds. So again, I'm just going to write it out like this so you can see clearly what it is. That's going to be 4 times 463. Then we'll have one oxygen-oxygen bond and then another one. So we've got two oxygen-oxygen bonds. So that's 2 times 146. So if you add that up, that comes to 2,144. Now onto the bonds made. Well, we've got OH bonds made. So we've got 1, 2, 3, 4. And then we've got an oxygen-oxygen double bond, and that is just 496. So if you add that up, that comes to 2,348. And then to give you your energy change, it's bonds broken minus bonds made. And that equals minus, and the signs are always important when you're doing energy changes. Even if they're positive, put in the plus sign. But in this case, it's negative, so it's going to be minus or negative 204 kilojoules. Explain whether the decomposition is endothermic or exothermic. Well, remember the answer was minus 204. So this minus sign is the clue. When it's minus, that means that heat is released. Therefore, it's going to be exothermic. If the sign had have been positive, then it would have been an endothermic reaction. On to D. I have to label these. Well, A is the activation energy, and it always goes from the reactants up to the peak of this hump. So even if it was an endothermic reaction, so say it goes like this, the activation energy still goes from the reactants line up to the peak. So back to the question then. B is the reaction pathway, and C is the energy change. Question 2. Write the molecular formula of B. Okay, just count up the number of carbons there are. So we've got 1, 2, 3, 4, 5. So we'll just put down C5, and then we'll do the same for the hydrogens. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's the molecular formula. Name the homologous series. Well, you can see here that they're all carbon-carbon single bonds. This is a saturated compound. So it belongs to the alkanes family. Which compounds are hydrocarbons? Well, a hydrocarbon is made up of the two words, hydrogen and carbon, and they only contain hydrogen and carbon. So that rules out A, because it's got oxygen. So B is definitely a hydrocarbon, as is C. It only contains carbon and hydrogen. D, yes. No, not E. There's an oxygen there, and it's not F because, again, there are oxygens. Which two compounds have the same molecular formula? So we're going to have the same number of carbons and the same number of hydrogens. If you have a look at A, you'll see there are 3 carbons, and E also has 3 carbons. A has 3, 4, 5, 6, 7, 8 hydrogens. Again, 3, 4, 5, 6, 7, 8 hydrogens, an oxygen and an oxygen. So these two, A and D, have the same molecular formula. Back to look. A is an alcohol and F is a carboxylic acid. It's got the carboxyl group here, and A has the hydroxyl group. And to convert an alcohol into a carboxylic acid, we use acidified. Again, we'll go back and have a look. Well, E is an alcohol, and the OH group is on carbon number 2. And it's got 3 carbons, so it's prop, and it's propan 2-ol. And then F, again, is 3 carbons, so it's based on prop. And it's a carboxylic acid, so it's going to be propanoic acid. So go back to E. You can see it's an alcohol, 3 carbons, so it's prop, and the OH group is in carbon number 2, so it's going to be propan 2-ol. And F is a carboxylic acid with 3 carbons, propanoic acid. Part 4, name the reagent to convert A, which is an alcohol. It's actually propan 1-ol, to F, which is propanoic acid. That's acidified potassium dichromate. Remember, it's orange, and when it oxidizes an alcohol, it turns to green. So I've already mentioned what type of reaction it is. It's oxidation. Compound E is an alcohol because it's got the OH, or the hydroxyl group. It's on carbon number 2, 3 carbons, so it's propan-2-ol, and then F is propanoic acid. Write a balanced simple equation for the complete combustion of C. Now C is but-2-ene. It's an alkene, carbon-carbon double bond. I'm just going to write down its molecular formula. So C4H8 plus O2 is going to produce carbon dioxide and water. That's the same for all of these compounds. They'll always produce carbon dioxide and water. And the way we balance these equations, the simplest way to do it is start off with the carbons. So we've got 4 carbons here. That means we'll have 4 carbon dioxides over on the right. Then we can look at the hydrogens. There are 8 on the left. That means we need 8 on the right. We can just put a 4 there. The last thing you balance are the oxygens. So you can see we've got 4 2s or 8, plus 4 is 12. So we need 12 over here. 6 will balance it. Part 7. We have to draw the structural formula of another compound that has the same molecular formula, C. Now C is but-2-ene, C4H8. And what we can do is move the double bond to one of the other carbons. So just move it either to the left or to the right. So what I mean is, let's say if I draw the 4 carbons, so it still has to have 4 carbons. Instead of having the double bond there, just get rid of it. I can move it to the right, or I could have moved it to the left. It's the same molecule, just flipped over. Now, every carbon must have 4 bonds, and we surround it with hydrogens because it's a hydrocarbon. So we have 1 here, 2, and 3. So you can see now that this carbon has 1, 2, 3, 4 bonds around it. This one has 2, so it needs another 2 hydrogens. And I need to be careful with these last 2. So this carbon has 1, 2, 3 bonds. It just needs 1 more bond. So I'm going to put it there, but I could just have easily put it down here. That doesn't make any difference. This carbon has already got 2. It needs another 2 bonds to make sure it has 4 bonds altogether. So I'm going to put then the final 2 hydrogens there, and you can see that it has 1, 2, 3, 4, 5, 6, 7, 8 hydrogens and 4 carbons. So it has the same molecular formula as C. And the name of this is but-1-ene. Part B, name substance X. Well, we're going from an alkene here to an alcohol. And if you look, you can see that an H and an OH has been added to it. Now, it's not water, because water won't react with the alkene, which in this case is ethene. So it's steam. Part 2, D is an alkene, ethene, and when it reacts with bromine water, the bromine water will go from orange to colourless. Part 3, the type of reaction occurring in Y. Well, you can see here that D is an alkene, that's ethene, and then the double bond breaks and we get these bonds either side. So it goes to this. So when you see this type of structure with the brackets and these bonds going through the brackets, that's a polymer. So if we start off with ethene, that becomes polyethene or polythene. So this here is addition polymerization. Just be careful here that you do not say additional, because it's not. It has to be addition. And then part 4, when you react any alkene with hydrogen, you turn it into the corresponding alkane. So D is ethene. When it's reacted with hydrogen, it becomes ethane. If it had have been propane, it would have become propane, etc. And what happens is that the double bond in the alkene breaks, and then 2 hydrogens add on across that double bond. So this is the structural formula for ethane. Okay, on to question 3 then. We have to name the ores. of a couple of these metals? Well, the main ore of iron is hematite, and the main metal compound present is iron 3 oxide, and the 3 is important, so don't just say iron oxide, because you can have iron 2 oxide, but it's iron 3 that's present. And the ore of aluminium is bauxite, and its main metal compound is aluminium oxide. Now in this question we'll have to look at the differences between the extraction of iron and aluminium from the ore. So pay careful attention to these bullet points. You've got to make sure that you answer these. So why is the method of extraction used? We're extracting aluminium, and that's extracted using the carbon monoxide. And aluminium is extracted using electrolysis. Carbon monoxide will not work, and it has to do with the reactivity of the metals. So aluminium is more reactive than iron, and that's why electrolysis has to be used. You could also say here that aluminium is higher in the reactivity series than iron. So that would be equally valid. But make sure there's a comparison, so you refer to the aluminium and that it's more reactive than the iron. So that explains why the method of extraction is used. The next thing we're going to do is look at the equations. So we'll do the aluminium equation first. And we start off with aluminium ions. They gain 3 electrons to form aluminium metal. And this is obviously what occurs in the electrolysis at the cathode. And then for the iron, we've got the iron 3 oxide, which is Fe2O3, reacts with the carbon monoxide, and the iron 3 oxide gets reduced to iron. And the carbon monoxide gains an oxygen to form carbon dioxide. It needs to be balanced, so we get a 3, and then we need to put a 2 there. That's the second bullet point. And then the third one is explain why the production of the metal is a reduction reaction. Well, if we look at the aluminium one first, we see that the aluminium ions gain electrons, and reduction is gain of electrons. Please make sure you say ions here. Don't just say aluminium gains electrons. You could use the symbol. I suppose you could say Al3 plus gains electrons. That's okay. But ions is key. And then on to the reduction of iron. It goes from Fe2O3 to Fe. So you can see here that the iron, or the iron 3 oxide, loses oxygen. And the loss of oxygen is reduction. You could also answer this last one in terms of electrons, because going from here, these are iron 3 ions, and obviously these are iron atoms. So you could say that iron ions gain electrons, reduction is gain of electrons, or you could say Fe3 plus gains electrons, reduction is gain of electrons. You're not told what to do, what way to answer it in the question, so just keep it as simple as possible. And so just answering it in terms of the oxygen is probably the simplest and safest way to do it. Balance sum equation for the combustion of sulfur, which is sulfur burning in air. So we've got sulfur burning in oxygen to form sulfur dioxide. Now it is asking us to include state symbols. Well, sulfur is a solid, oxygen is a gas, and sulfur dioxide is also a gas. Part 2, the appearance of sulfur, well, it's a yellow solid. And when sulfur burns in air, it burns with a blue flame. The sulfur dioxide that's formed is actually a colourless gas. On to part B. So we're looking at an equilibrium reaction. We can see the reversible sign here. So this reaction is an equilibrium. So we've got a state, how the yield of sulfur trioxide would change if the temperature is increased, and then we'll explain it. So first of all, we're going to state what happens. Now this is the clue. The forward reaction is exothermic, so that means it gives out heat. So this reaction does not want any further increase in temperature. And the question is about increasing the temperature. So the equilibrium system will move to oppose that change. So we increase the temperature. The forward reaction is exothermic. Remember, that's what this negative sign is telling us. Therefore, when the temperature is increased, the equilibrium will move to the left in the endothermic direction, because the exothermic and endothermic directions are in opposite directions. So if the exothermic is this way, to the right, then the endothermic reaction is this way, to the left. And if the reaction or the equilibrium moves to the left, that means that the yield of sulfur trioxide will decrease. So the reason it decreases is because the equilibrium moves to the left, because the reverse direction is endothermic. You could also say there, for that last point, because the forward direction is exothermic. Part 2. Now again, it's a question about equilibrium, but this time it has to do with pressure. So the pressure is being increased. And if we increase pressure, that means that the equilibrium will move to try and reduce the moles of gas. So count the moles of gas on the left. So you can see there are 3, 2 here and 1. That's 3. And there are 2 moles on the right-hand side. So if the pressure is increased, the equilibrium will move to the right, to the side with fewer moles of gas. And if it's moving to the right, that means that the yield of SO3, the sulfur trioxide, will increase. So here's the first part of our explanation. So the equilibrium moves to the right, to the side with fewer moles of gas. Or you could say, because it moves from 3 moles of gas to 2 moles of gas. Part 3, the formula for vanadium 5 oxide was made up of vanadium and oxygen. The V tells you the vanadium has a valency of 5, put it after the oxygen, and the oxygen has a valency of 2, so it's V2O5. Negative effects of acid rain, things like damages buildings, destroys vegetation, kills fish. On to D. Which one of the oxides is black? That's copper 2 oxide. Part 2, the reaction of copper with oxygen. Well, copper is Cu, oxygen is O2, and then it gives copper 2 oxide, which is CuO. And to balance it, put a 2 on the right and a 2 on the left. A basic oxide, well, a metal oxide is a base. So pick out a metal oxide, and there are 2. You could have magnesium oxide or copper oxide. A colourless gas which is toxic. Well, the gases here are carbon dioxide, carbon monoxide and sulfur trioxide. The 2 that are toxic are carbon monoxide and sulfur dioxide. And a gas that reacts with water to form carbonic acid, well, the clue there is the carbonic acid, and it's going to be carbon dioxide. The equation for that is actually CO2 plus H2O goes to give H2CO3. Okay, on to question 5 then. Suggest why the reaction between 10 and hydrochloric acid would not be used to prepare a gas jar of hydrogen in the lab. Well, if you look at these reactions, you can see with magnesium there are lots of bubbles, so there's lots of fizzing. And then from zinc, it's fizzing but not as much. And then with tin again, you've got the fizzing, but it is very, very little. So the reason we wouldn't use tin in the lab is because the reaction would be far too slow and it would take too long to make the hydrogen. Part 2, zinc plus hydrochloric acid goes to give zinc chloride and hydrogen. And then to balance it, would need 2 hydrogens and 2 chlorines on the left, so we put a 2 in front of the HCl. Part 3, explain which metal is the most reactive. It's going to be magnesium because you can see that it produces the most bubbles. And one physical property of hydrogen gas, so that's things like less dense than air, or you could say colourless, odourless, or insoluble in water. Part B then is about the electrolysis of dilute sulfuric acid. So we'll just sketch a diagram of what that would look like in the lab. So it looks something like this. We've got our electrodes here made from graphite. They're inert and they're good conductors of electricity. We've got our test tubes that were filled with water placed over the electrodes, and then as the gas goes into the test tubes, the water gets pushed out. So we can tell when the tube is full of gas. The hydrogen forms at the cathode and the oxygen forms at the anode. So we've answered B, part 1. Hydrogen forms at the cathode. And the half equation for that, now you're not asked for it, but I'm just going to write it in anyway. I'll put it over here to the right. We've got our hydrogen ions. We'll gain electrons to form a hydrogen atom, and then that happens twice. So there are 2 hydrogen ions. In total, 2 electrons are gained, and then the 2 atoms combine to form hydrogen gas. Part 2 is half equation for the formation of oxygen. Now, this one is different to the half equation in molten salts. So I have to start off with OH minus, and the oxygen comes from it. It's going to go into O2. Water is also formed. Now for this equation, you need 4 hydroxide ions, and they will lose 4 electrons. So I'll just put it in here. And to balance it up, we need 2 in front of the water. Just notice as well that we've got twice as much hydrogen formed as oxygen, and that ties in with the formula of water being H2O. There are twice as many moles of hydrogen as there are oxygen. Part 3 then, the test for oxygen gas is a glowing relights. C is an equation for the formation of ammonia. Well, ammonia is NH3, and we're told it's made from nitrogen, so it's N2 and H2. And let's see what else. Now we're told it's reversible, so it's important you put in a reversible sign and not an arrow. And then to balance it, we'll have to put a 2 in front of NH3 and a 3 there. Okay, so why is nitrogen unreactive? Well, nitrogen has got this triple bond between the atoms, and it is very, very strong, and it needs a lot of energy to break. D, calculate the volume of oxygen gas left over when this reaction has occurred. So I'm just going to write out the ammonia and the oxygen with their volumes underneath again. Now these two, as you can see, react in a 4:3 ratio. So if you have 40 cubic centimetres of ammonia, it will require 40 divided by 4 times 3 cubic centimetres of oxygen to react completely. So if I do that, so 40 divided by 4 is 10, multiplied by 3 is 30. So 30 cubic centimetres react. All of the ammonia reacts. And the question is, calculate the volume of oxygen gas left over. So it's going to be 40 minus 30, 10. Part 2, I have to calculate the volume of nitrogen gas formed. So I've written out the equation. And from the previous part, I know that 40 cubic centimetres of the ammonia react. And when it's gas volumes, we just simply look at the ratio. So it's 4:2. So that means 20 cubic centimetres of nitrogen form. Part 3, atom economy. So we're trying to work out the percentage atom economy of nitrogen. Now you need to be careful here, because this is the only time where you use the 2, the balancing number, when we're working out the total mass. So N2 is 28, and we've got 2 moles of them, so that's 56. And then what we'll have to do is work out the total mass of all of the products. Again, remembering to include the balancing number. So again, we have 2 times 28, so we've worked that out to be 56, plus 6 18s. So when you add those together, that gives 164. We want this as a percentage, times it by 100, and that is 34.1%. On to the last question then. We've got ethanoic acid is placed in the conical flask, and that's where the phenolphthalein is going to go. So the phenolphthalein in acid will be colourless, and then we're adding an alkali to it, so it'll go pink. So from colourless to pink. Part B, the apparatus that's used to place the acid into a conical flask is a pipette. C is, well, if you look at this part, that has lost the hydrogen, so it was ethanoic acid, and when it loses the hydrogen it becomes ethanoate. And here we've got potassium, so it's potassium ethanoate. If you look at the back of your data leaflet, you'll see that written as CH3COO minus. D, okay, we just have to work each one of these out. The first one is 20.9, then I've got 19.9, and lastly 20.1. Part 2, then we have to calculate the average titer. Now remember, we'd never include the rough titration, so we're going to use this one and this one. These are concordant values. They're within 0.2 cubic centimetres of each other. Also notice that they're within 1 cubic centimetre of the rough. So these accurate ones should be within 1 cubic centimetre of the rough. But as I said, you never include the rough when you're working out your average titer. Make sure you have it here to decimal place. Calculate the concentration of ethanoic acid. So I've just inserted here the introduction to the question, which we'll have to use shortly. Now we've got the potassium hydroxide, which is 0.045, and we've got the volume of the potassium hydroxide that was used. We've got 2 values for it. That's where we have to start. To work out the number of moles, that's going to be 0.045 times our average titer, which is 20, over 1,000, 0.0009. The balanced equation for the reaction is shown here, and as you can see, it's a 1-to-1 ratio. So the moles of ethanoic acid are going to be the same. Now we've got the moles of the acid. We know the volume, 25 cubic centimetres. We can work out the concentration. So concentration equals moles divided by volume, and then we're going to times that by 1,000. So it's 0.0009 over 25 times 1,000, and that gives an answer of 0.036. Part 4 then, to finish this off, we've got to convert this into grams. So now we're using moles equals mass over RFM. Well, we have worked out the moles, and we can work out the RFM of ethanoic acid. So multiply these two together, that'll give us the mass. Now the RFM of ethanoic acid is 60. So just simply multiply that by 0.036, and that gives 2.16 grams per cubic decimeter.